Hello, this is lecture 17, part 1. In previous lectures, we discussed solutions of a linear ordinary differential equations of higher order with constant coefficients. And now we are going to consider some applications. So this lecture is about applications of linear ordinary differential equations with constant coefficients. And of course, there are many applications. Here, we are going to consider mechanical systems. We are going to consider several cases. We are going to start with a certain situation, and then we will keep adding conditions. So the first case we are going to consider undamped spring mass systems. Okay, so we have a spring. I'm sorry, my drawing is not very good. So we have a spring in natural position. So we attach this spring into the ceiling. So this is ceiling. We attach one end of the spring into this ceiling. So this is spring in natural position. And now we consider attaching a mass. So let me. So the same spring, this is the ceiling. Same spring, but now we add a mass. So the spring is elongated. At the end of it, we have mass M. So the natural length of the spring, when you add this mass, it is elongated too. So this mass is so when you attach the mass, it is elongated by a certain amount. Let's call this L. Okay, so and we consider this position when we attach the mass. This is in here the mass in the second drawing, the mass is in rest, mass M in rest. So the system is in equilibrium. So system is in equilibrium. Okay, so in this equilibrium position, we consider forces acting on this mass. So there is the force applied by this spring in the upward direction, and there is the gravitational force on the mass in downward direction. So Hooke's law, this is from physics, restoring force applied by the spring, is directly proportional to the contraction or elongation distance in this diagram. It is the length L of the spring. Okay, so since we say it is directly proportional, it means there is a proportionality constant involved. We are going to call it K, proportionality constant, proportionality constant of the spring. And if you know that at equilibrium position, the spring is elongated by distance L, and it has mass M, then this contraction force, restoring in equilibrium, restoring force is equal to um, the gravitational force, is equal to, I'm sorry, one moment, to gravitational force on the mass. So gravitational force is m times g. G is the acceleration due to gravity, and this should be equal to the restoring force of the spring. This is the proportionality constant K times the elongation distance L. So of course here m is the mass of the object. And g is the gravitation acceleration due to gravity. So from this, we can figure out this constant K. The constant K, in this case, the proportionality constant, is m times g over L. Why do I write it this way? I don't know. M g over L. So using this information, we can figure out the proportionality constant K. Now, what we want to do is we consider this object moving up and down. Imagine pulling it down a little bit and then releasing it with a certain velocity, and then the mass is going to start moving up and down due to the restoring force of the spring and the gravitational force. It will move up and down. So if the object is moving up and down, our question is, we want to understand how it is moving. So let ut be the position of the object at time t. And we consider the equilibrium position corresponds to position 0. So at the equilibrium position, the position of the object we consider to be 0, and then when it's moving up and down, we denote the position by u of t. Okay, so when the object is at position ut, okay, force exerted by the spring is k times u, because the elongation distance is going to change now when the object is moving up and down, and the position gives you, since the equilibrium position is, okay, of course there is the initial, let's see, there's the initial elongation, and this position corresponds to u equals 0. And if the object is lower than this position, then we only consider the force exerted on the object by this change of distance, just u. We don't consider the amount L, because L is the elongation when the mass is at equilibrium, and that force is equal to the gravitational force. So they cancel each other out. The gravitational force on the mass m at position u equals 0 is equal to the force exerted by the spring. So they cancel each other out. We don't need to consider, we don't need to take them into account. Okay, so we only consider the part of the force exerted by the spring on the object caused by this distance u. And now, of course, Newton's law of motion. Force on the object is equal to its mass times the acceleration. Now, the force, the gravitational force, this force due to the motion is going to be in one direction, and the force exerted by the spring is going to be in the opposite direction. In opposite direction. Direction of k times u. So we have m times acceleration a, which is of course the second derivative of the position, equal to k times u. They're in opposite direction, though, so they should be equal to each other. Okay. Wait, no. I'm sorry. This is the total force. Okay, so this is the total force on the object. Force equals ma. So it is m times u double prime. Acceleration, a is acceleration. So A is the second derivative of u with respect to t, which is u double prime. But now, on the other hand, the spring exerts this force in the other direction. So this is equal to minus k times u. Why the minus sign? Minus sign because the spring exerts a force in the opposite direction of the movement. Direction of motion. If the object is going down, the spring tries to pull it up. And if the object is moving up, then the spring is compressed, so it tries to push the object down. So this force applied by the spring on the object is in the opposite direction of the motion. So that's why we have the minus sign. Okay, so m is the mass of the object, of course, constant. K is the proportionality constant, which we figured out up there somewhere. Yes, K is mg over L. So then our equation, m u double prime plus k u equal to 0. So this is a linear second order homogeneous ordinary differential equation with constant coefficients. And we know how to find solutions of such equations, right? We consider the characteristic equation. So let me rewrite the equation here. Mu double prime plus Ku equal to 0. Remember, K is mg over L. M is the mass. So K and M are constant. So we consider the characteristic equation. M lambda squared plus K equal to 0. Okay, K and M are constants, but more than constants, they are positive constants. M is the mass, G is acceleration due to gravity, L is the distance, elongation distance for equilibrium position. Everything is positive, okay? So when we solve this equation, lambda squared equals minus K over M. So K over M also equal to minus G over L. This is not 9, G. It's hard for me to write the small letters. Minus G over L. So this is a negative constant. So this is negative. So lambda equals plus or minus I times square root of K over M. This number we denote by omega 0, K over M. This is called the natural frequency of the system. natural frequency, because the solutions, since we have complex roots, the solutions are going to be in terms of sine and cosine. Solutions are purely imaginary, real part is 0. So solutions, solution of the ODE is C1 times cosine omega 0 t plus C2 sine of omega 0 t. You see the number omega 0 affects the period of the function. So the period of cosine and sine is 2 pi, but inside cosine and sine, when you use omega 0 t, it means the period is 2 pi over omega 0, right? So the period changes with this number omega 0. That's why it's called the natural frequency. Okay, so note that small frequency means when omega 0 is small, then your period is large. That means your graph is more sparse. But if the frequency is high, then the period is small. It means your graph is going to be more packed. I will try to show you some rough pictures. Okay, but first I'm going to rewrite this solution in another form. Now, C1, in this solution, C1, C2 are constants. Consider the point C1, C2 as a point in the XY plane. And express them in polar coordinates. So C1 is R times cosine theta, and C2 is R times sine theta. This R is the square root of C1 squared plus C2 squared. So instead of using C1, C2 constants, we use the constants R and theta. Of course, R and theta are constants. But now our solution U, instead of C1, we write R cosine theta, then cosine omega 0 t, plus R times C2 is sine theta times sine omega 0 t. So if you take out R, cosine theta cosine omega 0 t plus sine theta sine omega 0 t, you can write it as cosine of omega 0 t minus theta. So you see, you can express the solution using just the cosine function, cosine wave. This number R is going to be the amplitude of your amplitude of your function. Now it depends. It depends on C1, C2. The constant C1, C2 depend on initial conditions, of course. To find the constants, we need initial conditions. And what are the initial conditions? U, the value of U at time t0, and the value of the derivative of U, or the velocity of the system at time t0. This may be the time time t equals 0 when the object starts moving. So the constants depends on the initial position and the initial velocity of the object. And depending on the constants, we have the amplitude of the system. Now, period, as I said, is 2 pi over omega 0. Some more names. Okay, this angle theta is called the phase. So period is 2 pi over omega 0. I call it omega 0, right? Yes, omega 0. If omega 0 is small, period is large, graph is, if omega, then the period is large, graph is sparser. So we have a graph like t u. So at the initial time, at t equals 0, let's say we have a certain position and certain velocity, and then we have a cosine wave. Something like this. So amplitude is R, remember. I'm not, okay, doing a very good job of this. I'm sorry. Okay, so something like this. Okay, amplitude is R, so from minus R to R, we have a certain period, which is 2 pi over omega 0. Now, if omega 0 is large, so you see in the first case, omega 0 is small, so we have small frequency. The same point appears in a certain interval, the same value appears in small quantities. But if omega 0 is large, then the period is small. Graph is denser. So you're going to have a denser graph. Again, from minus R to R, but now the same value is going to keep occurring a larger number of times. So omega 0 is large frequency. Okay, in the first case, frequency is small. In the second case, frequency is large. All right, so this is undamped spring mass system. If there is no damping, then the object is going to keep moving up and down from the equilibrium position. You can consider, so U, T, so the T-axis corresponds to equilibrium position, U equals 0. So you see the object is going to keep moving up and down of the equilibrium position when there is no damping. Now, we consider the second case now, effect of damping. Damping it means it's some other force on the object which slows it down. So this may be due to friction, or maybe this movement is some viscous object in viscous liquid, some viscous medium. So we have damping force. It may be due to friction or viscous medium or something like this. Okay. Of course, we need to make some assumptions. We assume that the damping force is directly proportional to the velocity. Velocity v, but remember, v is the derivative of position with respect to t, so it's u prime. Velocity of the object. And so that means we have some proportionality constant. We call it gamma, proportionality constant. Now, how is this going to change the equation? So on one side, we have again mu double prime coming from Newton's law of motion. In the other direction, we have the force exerted by the spring and also the force due to this damping force. Okay, so proportionality constant. The damping is also going to be in the opposite direction of the motion. It will try to slow the motion down, so it comes with the negative sign. So our equation is mu double prime plus gamma u prime plus ku equal to 0. So this is again homogeneous second order ordinary differential equation with constant coefficients. A constant, and all the constants are positive. So how do we find the solutions? We consider the characteristic equation. The characteristic equation is m lambda squared plus gamma lambda plus k equal to 0. So the solutions are going to be what? By quadratic formula, minus gamma plus or minus square root of gamma squared minus 4mk divided by 2m. So the solutions depends on the discriminant. Of course, discriminant lambda squared minus 4mk. So we are going to consider the cases. The first case, when discriminant is positive, is called overdamped. Okay, so discriminant positive means we have lambda 1, lambda 2, real, distinct roots. Okay, Uh, Now, note that, okay, so lambda 1 is going to be minus gamma minus the square root over 2m. So this is negative. Remember, all the constants, m, k, gamma, are positive. We have minus gamma minus the root, that's negative. The second one, minus gamma plus the square root, gamma squared minus 4mk over 2m. This is still negative because, okay, 4mk is positive. The constants m and k are positive. So gamma squared minus 4mk is less than gamma squared. You're subtracting something. And that means the square root is less than gamma. So minus gamma plus the square root is negative. Okay, so both roots are real, negative, distinct roots. And the solution, C1 e to the lambda 1t plus C2 e to the lambda 2t. Okay, now since one thing we note about the solution, since both numbers, lambda 1 and lambda 2 are negative, the limit as t goes to infinity of this function is going to be 0. So you see in the overdamped case, the position is going to approach to the equilibrium position. Okay, and you can consider this equation in detail. There is at most one local minimum or maximum. So typical graph would be, oops, I'm sorry, one moment. So a typical graph there may be some motion in one direction, but it's going to reach, say, there is upward motion, but it's going to reach its maximum and then it's going to approach to 0. Okay, or the maximum, it may be minimum, of course, depending on the constants. Again, it depends on the constants, C1 and C2, and they depend on the initial position and initial velocity. Of course, it may be like this. Maybe movement in the other direction, it reaches the minimum, and then it approaches to the equilibrium position. So there is no up and down motion. The system is overdamped, so there's no up and down motion. The initial motion may be in one direction. It reaches the maximum or minimum in that direction, and then it will start moving in the opposite direction and approach to the equilibrium. Never pass the equilibrium again. Okay, when the system is overdamped. Okay, for this video, I'm out of time. We are going to consider the other cases in the second part of this lecture. So that's all for now.